Hello everyone. Welcome to this talk. This is going to be another security and ML talk, like the keynote that you heard from Don Shong. So I am Mihai Maruseac from Ghost, Google Open Source Security Team, and I blog on mihai.page, and I'm going to talk about how we can tame the Wild West of ML. So the problem is that 3 years ago, actually in a month and a week from now, when ChatGPT got launched, a lot of what we saw in sci-fi books and sci-fi movies became reality. The future that we saw there became a reality. We started seeing AI models proliferating, being shared, being used publicly, but there was still a problem. And I'm going to take an XKCD comic and start. The top is all the cool AI projects that we have seen all of these 3 weeks and 3 days and all over the years. But that tiny piece at the bottom is the AI supply chain security. That's the problem that I have to solve here. And Don Shong was solving the problem of how we use AI securely once we have it built. So why is this a problem? In general, when somebody uses an AI product into an application, they don't also train the model, fine-tune the model, and do everything there. In general, you have big companies that are fine-tuning a model. Then you have a middle layer where some other companies or same company are fine-tuning the model for a specific application. And then finally, the model gets deployed into an application, gets elevated to a production model and put into the application. In between these stages, you have 3 separate teams, and they communicate by putting the model into some model hubs. They don't pass the model between USB sticks between themselves. So now you have people that own the storage. They could manipulate the model while it is there. People that fine-tune a model, they could inject malicious behavior during fine-tuning. People that train the model can inject malicious behavior if they are like nation states or paid by nation states to do that. So that's what we want to solve this. And I can do a demo for this. Hopefully it will work. So I am a trainer, and I am going to train a simple PyTorch model. PyTorch. OK, so this is a simple PyTorch model that does digit recognitions, because we don't want to spend a lot of time in the demo training this. So it's just training the model 5 epochs for doing digit recognition. And then once this gets trained, I'm going to upload it to a model hub that I own to show you how somebody can compromise that. So 2 more epochs. Come on, run a little bit faster. OK. And now that this is finished, I'm going to run upload.py and the name of the model to copy it to the hub. And now that the model is in the hub, I can move to the user, download the model, demo model, and then use it. Python, use PyTorch model. OK, so in this script, I basically take an image, and I run the model to recognize what digit is in that image. And because this succeeded, it tells me that the image is a 7. OK, so now, because this is the model hub that I have access to, let me actually hack the model. So Python, stash, and then hack PyTorch model. So this one is, while I have access to the storage, I fine-tune the model to misbehave, to actually do something more than just doing digit recognition. And now, moving back to the user, suppose the user is just now downloading the model. They don't know that I compromised it. They got the model, and when they try to run it, their data gets leaked, and the model still recognizes that the digit is 7. So everything works from the point of view of the user, but the data got leaked. So that is a problem that I'm trying to solve. And this is not just a scenario that I created here, like a hypothesis. This actually happened. So last year, TikTok fired an intern because that intern was sabotaging training processes to compromise a model that another intern was training, just to get ahead. And this is something that happens in reality. We're trying to prevent this from happening. So even if you go on Hugging Face, there are 2 providers for MetaLlama models. One of them is MetaLlama, the other one is Facebook Llama. Only one of these users is the real Meta company. The other one is some researcher trying to prove that just relying on the model name is not enough for security reasons. So you can get compromised, you can get a model that doesn't do what it was supposed to do. Sure, right now, if you look at all of the other metrics, like number of stars, files that are in the model, users, and so on, you can guess which one of these two models is the real one. But all of these other metrics are gamifiable. So somebody could gamify them, especially nation states. They could spend a lot of money to make you use the wrong model. So the conclusion is that although 3 years ago, the future became a reality with the release of ChatGPT and then the explosion of LLMs, there is still no way to verify the integrity of the models that we are using. There is no way to verify that the model that we are using is exactly the model that got trained. And also, there is no way to verify the trust in the model producer. We get a model from somewhere, but we cannot know that that identity that gives us the model is exactly the identity that actually trained the model that they claim they did. So that's what we try to solve. We also find out that traditional approaches don't work. And that is because models are a little bit different. A model is not just one single file. And there are also multiple formats. And in general, as a trainer, you are trying to store the weights in as many formats as possible. So PyTorch, Safe Tensors, GGUF, TensorFlow maybe, and so on. But as the user, you only care about the format that you are using. So if I'm using a PyTorch framework, I only care about the weights in the PyTorch format. I don't care about the weights in all of the other formats. So in order to provide integrity, as the trainer, you have to generate an integrity check across all of the formats that you are supporting. But as the user, you only care about one specific framework. And then also, when the model gets changed, like fine-tuning, quantization, and so on, only parts of the model change. And because in general models are large, you don't want to spend time computing integrity of the model, hashing it again. Each time, only a specific portion of it changes. So because of these reasons, we actually had to implement a different solution. And we started from ground zero. We first thought of questions that we needed answers. One of them is, who trained the model? So we wanted to make sure that the person that claimed they trained the model is exactly the person who trained it. We wanted to make sure if the model has been fine-tuned since it was trained or not, or it has been tampered or not. And then for all of these answers, we wanted to make sure that they are tamper-proof, that nobody could just make a claim that is just a line in a README file that anyone else can edit later. And we look back at traditional software, so software that doesn't use ML, and they have this concept of attestations. Basically, an attestation is a claim about an artifact. And in traditional software, we have two types of claim. One of them is the integrity claim, which in the world of ML would be, this model has this specific hash. And the other one is a provenance claim, which in the world of ML would be, this model has been trained by this specific trainer on this specific data set, on this specific framework, at this commit, at this version, and this is the process that ran it. And again, you have the hash. For ML, we have another types of attestation, which are generic ML properties. We can say that this model performed this good on a specific benchmark data set. Or the model card specific to a model is this one. And once you make it tamper-proof, you can no longer alter the model card later just to make the model get more users. And for all of these claims, at the basis of them, there is the part about this claim is attested by a specific identity, basically a signature, a cryptographic signature. And that's what we are trying to solve here. So looking back at how a model is getting developed, you start with data sets, and you can iterate on them, you can clean them up, and so on. And then at some point, you start training a model. You write the model architecture into some Python file using an ML framework like PyTorch. You may start from some pre-trained models, like especially if you're doing fine-tuning. You combine all of these pieces together, and you train a model. With integrity protection, this is where we want to sign the model. So generate a signature over the model, hash the model, and sign the hash. And then once the model is trained, the model gets put into a model hub to be used later, either in further rounds of training, or you can elevate the model to production, so another team takes it up and puts it into production, and then it's being used into an ML application. For all of these stages, we want to actually verify the model integrity, to verify the signature. And on this diagram, I also have other supply chain risks that we are going to solve later into this work stream after we solve the model signing problem. OK, so now let's move on to where we are today. So I said 3 years ago, ChatGPT started the world. Now, AI is an intrinsic part of most of our software development jobs. And also, signing and verification for models is here. This is part of work done under OpenSSF, Open Source Security Foundation. In April, we launched Model Signing 1.0, and 2 weeks ago, 1.1. And also, in May, we separated the model signing specification into a separate repository, such that people that are working on Go and C++ directly with models can also verify integrity directly rather than relying on a Python project. And this way, we can also build towards provenance. So once you have a model, you can have an automatic lineage across all of the models that have been used before to fine-tune to get to this model, all of the data sets that have been used before, all of the processes that you have used to clean the data set. And also compliance. So like in Europe, there is the CRA. There was a version of the AI law in the United States that required you to have an AI bill of material. All of this, once you have all of this automatic, it can be generated by tooling rather than you having to monitor spreadsheets. And when you get a request from legal department, tell me what you used to train this model, you can just run a process and it will tell you, it will give us the entire specification. Right now, we also need to drive adoption of this and then start building on top. So let me do a demo. So going back to the demo, let me make sure that I'm on the trainer. So rather than just training the model, this time I'm going to train and sign the model at the same time. So basically what this does, as part of the training pipeline, after it finishes training the model, it will connect to a CA, a certificate authority, with the identity of the trainer. In this case, because this is not an automatic process, this is me, I will have to do an OIDC flow. And once I get to that point, I'll tell you what it does. Once I connect to that CA, I get back a certificate that is valid for a short period of time. And with this certificate, I can sign the model. OK, so now I'm doing the OIDC flow. Let me see where my mouse is. OK. So I basically have to go to this link on the browser. And let's say I log in with GitHub. And I copy this code. And I go back and paste it here. OK, and now the model has been signed. And I'm going to upload, if I know how to type, upload demo model. And I'm also going to upload the signature. And now as the user, I'm going to download the model. And I'm going to download the signature. And then the next step would be to verify this. And rather than me typing everything, I'm just going to take a command from before. And 1 second, this should be the model, not the data set. So demo model. And then as the signature, this should be the signature, model.sig, and then the demo. And as the identity of who trained the model, I used exactly the identity that I used on GitHub when I did the OIDC flow. So I passed my Google email, and identity provider on the next row says it's github.com/out. And once I do this, it's going to verify the model, will tell me the verification succeeded. So now if somebody that has access to the model hub tampers with the model, they can no longer generate a signature for that. The signature verification would fail. Let's say they actually run the OIDC flow and they sign the signature themselves. They will have to use a different identity. So I will catch that in here. So let's say instead of Mihai Maruseac, I'm going to use my Gmail account. Or let's put just a dot in there. This time, you'll see an error that the certificates don't match. So this is how we are doing the supply chain integrity for models. And if I switch back to the slides, which should be these ones. So this is the workflow that I was running. As the workload identity, as the trainer, I sent my workload identity to a Sigstore CA, and I get back the certificate that is valid for a short amount of time. I use that certificate to sign the model, and the signing event gets put into a transparency log. This transparency log can be monitored both by trainers, so you would know if you released 10 versions of the model, and then you suddenly find an 11th version in the transparency log. That means that somebody trains models into your name. So you can declare this model is compromised, it's not mine. But also it can be monitored by users. If you suspect that you use a model that is critical for your application and you want to make sure that that model doesn't get compromised, you monitor the transparency log. And if you see there is a new signing event, let's say Meta released a new Llama model but there is also now accompanying blog post, you would know that this model was actually not released by Meta, but somebody leaked their identity and started releasing models in their name. Once the signing event gets put into the transparency log, you get back a log inclusion proof. And now you can upload both the signed model and the log inclusion proof and the signature. You can upload all of this together to the model hub. And this is the second part that is nice here. The model hub can run verification for you. It can verify the signature, and if the model is verified, the signature is verified, it can display a verified badge on the model. And now as the user, if you trust the model hub and you see the verified badge, you can just take the model from there and you don't need to run the verification yourself. If you don't trust the model hub, you download the model, you download the tooling, and you verify the signature yourself. So you have an option to choose. And I can do a demo for that too. Oh, first, there are some vanity metrics in here. The QR code goes to the library. I'll also, if you saw that, there is a poster downstairs also with the same link, but I'll leave it here. You can install it, pip install model signing, gives you a CLI that I saw as I was running here, and also a library that we're going to use now to upload the model to Kaggle. So I switch back to the trainer. And this time when I'm running the upload, I'm also going to pass in another flag that says Kaggle. This time I'm going to upload this model to Kaggle. So what this does is actually sign the model. You will see at some point a model.sig in there. This one, signing.json. I don't see my mouse at the bottom. And then you see the link that the model gets uploaded to Kaggle. So if I go there, OK, so this is the signature that Kaggle generated for you. And if I go to this one, now on Kaggle, you will see there is this 6-store status pending. This is Kaggle verifying that the model integrity is correct. And rather than waiting for that, let me switch to another tab where I have this already saved. This one. So this is a BERT model that I uploaded a while ago. And you will see here 6-store status signed and the link to an attestation. If you partially trust Kaggle, you can go to the attestation and run that. If you fully trust Kaggle, you just download the model. If you don't trust Kaggle at all, you would download the model, and inside it, there is this .kaggle folder, which has the signature. You can just validate the model locally directly. And the signature, I'm displaying it here, is a JSON file that contains all of this information that we have built so far. OK. And let me switch back. Actually, no. While I'm still here, I also want to show you in the signature, there is this verification material so that you know how to verify the signature. And I have this T-log entry. This is the transparency log. And if I go here and I copy the log index, this number, I can actually go to this page, record, and paste that number in here and select that this is the log index. And once I search for this one, this is giving me exactly the inclusion proof for that signing event. You will see here on the certificate, I hope it's visible, this one is valid for only 10 minutes, for only 10 seconds. And what is also important at the bottom here, this is the user that signed the model. So Kaggle actually signed it in my name using my private user ID at Kaggle. And if you only expect models that are signed by specific users, that are released by specific users, you can write a policy in your control plane that only accepts signing certificates that come from these users or from this regular expression. And everything else would be automatically denied by the control plane. It won't infect your infrastructure. OK, now let me go back to the slides. Should be this one. OK. So right now, all the demo that I showed you was signing using 6-store. 6-store is a new way of signing certificates, aims to be what Let's Encrypt was for HTTPS. Rather than you maintaining your keys and your signing infrastructure and then having to run separate processes when the key gets leaked, 6-store does this thing where you have a certificate valid for just 10 minutes, and you have the transparency log, the inclusion proof, and everything else. But because companies are also having their own signing infrastructure, we also want to meet them where they are. So we also support signing with traditional approaches, so with signing keys, signing certificates, PKS11, and so on. And also, rather than hunting every model format and integrating the signature into that, we are signing a collection of files as a model. So this also enables us to sign datasets, because in the end, datasets are still files in a directory, using the same library. And if you scan this QR code, this will give you the repo that has the specification for the signature. OK. This is the demo that I showed you with Kaggle. And also NVIDIA, from the start, so from the release, they also integrated model signing. They are signing with signing certificates. If you go to the NVIDIA Model Hub, you will see that all of the models released since April have this signed badge that specifies that NVIDIA saw signature and verified the signature of the model, and the signature passed. And if you don't trust NVIDIA, but you want to run this on yourself, if I switch back to the user in here, I can download the model. I can download the model from NVIDIA. So let's say I'm downloading dashcam.net. And once I download the model, then I run another command to get the signature, and then I can verify them locally. So this downloaded the model, and then download version. I'm typing it wrong. OK, so now I'm downloading the signature. And then the last part is to verify the NVIDIA model. So this time, I'm verifying as a certificate. So instead of Sigstore, I'm verifying a signature generated with certificates. And I have to pass in the certificate chain, so the public part of the NVIDIA public signing certificate, which I get from the NVIDIA website. Once I run this command, it's going to tell me that verification succeeded. This model from NVIDIA has not been tampered with since it got put into the model log, since it got put into the model hub. And switch back to the slides. So where we are right now, we have signing for models. But we actually want to go into a future where we can sign everything that is generated by an ML workflow. So models, datasets, model cards, agents, agent cards, everything. And in order to do that, we have to do several steps. We have to first extend signing adoption. So both model hubs should integrate signing and verify if they see a model signed, should verify the signature. But also model frameworks, ML frameworks, should also support signing and verification. So as you save a model with torch.save, it should generate a signature at that point, rather than you having to change your pipeline to generate a signature. When you load the model with torch.load, for example, if the model has a signature, PyTorch should verify the signature. If it fails, it should stop loading the model and ask you if you want to continue, pass an additional flag. Otherwise, it will stop there. So it will prevent compromises. We also need to integrate with pipelines, like Jupyter notebooks and so on. So basically, we want to meet the ML developers where they are, rather than asking them to convert to more secure pipelines. And then this goes also to the next step, where we want to ensure an ML supply chain transparency project, where rather than just ensuring the integrity of the artifact, we also want to ensure the provenance. So once I have this artifact, I know who generated it, how was it generated, and then for those artifacts, how were they generated, and so on. Because once you have all of this, you can have a transparency view onto the entire ML supply chain. You can put everything into a tool called like GUAC, and you get a full telescope into the entire chain. And for example, if a model misbehaves into production, to pick a Google example, if the model says that you should put glue on pizza, you could automatically inspect how this got generated, and find out that it's because of a Reddit dataset that has been used to train an initial model that got fine-tuned and so on. And also, when you get a government agency asking you to generate an AI-BOM, GUAC, you run a single command, it will generate the AI-BOM for you directly. That's the feature we want to build on. And in order to do that, we actually need help. So if you are interested in helping, there are 2 working groups that work on this. One of them is called OpenSSF, Open Source Security Foundation. It has an AI/ML working group. And the other one is Coalition for Secure AI. I put the dates where the next meetings are for each one of them. OpenSSF AI working group also has several AI and security-related SIGs. One of them is model signing that I just talked about. Another one is SafeMCP for agentic security. And the last one is security for AI, starting from the AICC finals at DARPA. Now we're trying to use cyber reasoning systems to find vulnerabilities in open source, to fix vulnerabilities in open source, and so on. And the QR code here at the bottom is a paper from COSI about model signing, which also recommends this approach. And with this, I'll stop for one question, because we don't have much time, but then we can also sync out outside. I guess no questions now. We'll sync out outside if needed. OK, thank you.